The Northern Lights, one of the great celestial phenomenon of the night sky. Witnessing the aurora is a bucket list experience for people all over the globe, and those who have witnessed a good aurora show never forget it. For photographers, the aurora are one of the most prized of all natural subjects, and they flock to the cold, frozen north every aurora season to catch this elusive wonder. The Northern Lights can be a tricky and elusive trophy to chase. Many times in my early Alaska years, I'd go out and freeze my fingers off, only to come back with nothing. I was determined to learn as much as I could about aurora science to keep this from happening again. Today I'm going to talk about a few basic numbers that'll make you an efficient and effective solar storm chaser. Don't waste time on fruitless chases staring at blank skies. Know exactly when and where the Northern Lights are going to dance. Whew! Cold day out here today. KP values are a composite number designed to give you a rough idea of what to expect from the Northern Lights. They range from 0, which would be inactive, to 9, which is extreme. To give you an idea of what exactly it means, a KP of 1 or 2 would probably be enough in a place like Fairbanks, where the Northern Lights are common. Where I'm at, 60 degrees latitude, a KP of 4 is about the minimum I look for before going out on a chase. A KP of 6 is probably strong enough that you might see it in Colorado. The conditions are just right. In the famous 2003 Halloween solar storm, we saw KP values of 9+, and the aurora were visible in Dallas, Texas. Fun fact. Perhaps the strongest known solar storm in relatively modern history was the Carrington Event of 1859. While we don't have a solid KP number for this event, it was strong enough to be seen in Mexico City. Telegraph wires exploded in flames. Supposedly the aurora were bright enough in Boston that one could read a newspaper under their lights. It is thought that if such an event happened today, it could do major damage to our electric grid. The solar wind speed is another factor that determines how strong a given display of aurora will be, and how much the lights will move, or dance, as people like to say. A normal solar wind speed tends to fall around 300 kilometers per second. Over 600 kilometers per second would be high, and over 900 is extreme. The Interplanetary Magnetic Field, or IMF, is defined as the component of the solar magnetic field that is dragged outward by the solar wind. The strength and orientation of the IMF play a major role in how we experience the aurora. The first number we will talk about is the BT. The IMF BT measures the overall strength of the IMF. Anything under 10 would be considered low. 10 to 20 is moderate. 20 to 30 is high, and over 30 is very high. As one would guess, the higher this number, the better. But decent and photogenic displays of aurora can be seen even with BT values below 10. Last but certainly not least, we come to what I consider the most important number of all when it comes to solar storm chasing, the IMF BZ. The BZ is a measure of the orientation of the IMF. Since the IMF is a magnetic phenomenon, it has polarization, and like all magnets, if they are oriented one way, they attract, and the other way they repel. Without getting into the weeds explaining how the BZ works, the simple way to think about it is that the IMF needs to be oriented to the south, to attract charged particles into the Earth's atmosphere. The BZ will be a negative number when it's oriented to the south. Any positive value will repel all but the strongest of solar storms. This number, however, is constantly shifting and can change rapidly even from minute to minute. This is what causes the aurora to fade and erupt seemingly unpredictably. Some nights the BZ stays pegged in a relatively stable orientation one way or the other. Other nights it jumps back and forth constantly. One of the best aurora chases I have ever had, February 26, 2023. The rating was pegged at about -10 the entire night, and the aurora started early and went on until it was too light to see them in the morning. Other nights I've seen great displays only to have them fade away as the BZ drifted north just when it seemed they were getting started. Luckily, however, we launched the DSCOVR satellite in 2015. The DSCOVR satellite sits at the Sun-Earth L1 Lagrange point. Its entire purpose is to measure the solar winds and detect solar storms. With its distance from Earth and the speed of the solar wind, we get about 45 minutes of lead time where we can see changes in the solar wind and IMF. That means if you are home or someplace warm, you can monitor the IMF, particularly the BZ, and have a pretty good idea exactly when the sky will erupt with lights or fade into nothing about 45 minutes before it happens. So there you go, a basic introduction to the numbers and ingredients that define solar storm chasing. There are a number of apps you can download to monitor this data, and all that remains is for you to get out and take incredible images of those dancing lights. Until next time, you stay interesting, folks. I'll be boring enough for both of us.